Welcome! Today we're going to look at section 7.6. This is a fun section. It's about problem solving using rational equations. So we're getting to a few applied problems where the techniques that we've been learning are very useful. Okay, so before we get to the real involved applied problems, we're going to do just some simple ones involving proportions. All right, before we get to proportions, you need to know some vocabulary. What is a ratio? A ratio is just a quotient of two numbers or two quantities. For example, 3/7, that's a ratio. 7/3 would also be a ratio. It can also involve variables, so it could be something such as x over the quantity x plus 5, or the reverse of that. Now, a proportion is a statement that says that two ratios are equal. So it's when you set two ratios equal to each other. So notice up here I have a comma, down here there's an equals. So that's the difference between a ratio, which is a single fraction, and a proportion, which states that two fractions are equal. Okay, now in a proportion, cross products are equal. Now this is something that students often overuse, so don't go too crazy with this. But, and I want you to understand why it works. But the neat thing is you can cross multiply. Okay, so if you have a ratio, or a proportion rather, such as A over B equals C over D. Okay, usually we're solving. And when you're solving, you want to eliminate the fractions and get rid of those denominators. So how you do that is you multiply both sides by the lowest common denominator. Okay, in this case, the lowest common denominator would be B times D, their product. Okay, so if I multiplied both sides of this ratio here by BD, so BD on the right and BD on the left, well then on the left side the B's cancel, and on the right side the D's cancel. And so what we end up with is A times D equals B times C. Okay, so what you'll notice is that you can really just go straight from here to here if you see that what's called their cross products are equal. So cross products mean you multiply those two together, A times D, and that equals the product of these other two, B times C. Okay? So here, let's use this idea here to check on these proportions down here and see if they are in fact equal. Does 2/3 equal 6/10? Well, let's check by using cross products. So if I was to multiply both sides by 30, okay, what I would get is the same thing as if we cross multiply. So I'm going to cross multiply here the 2 times 10 and say that equals 3 times 6. So is it true, does 2 times 10, I'm going to put a question mark, does that equal 6 times 3? And the answer is no. 20 does not equal 18, so no. So that one's a false statement, that first one there. Now on this next one, let's see if we cross multiply. We would have 4 times 15. Does that equal 6 times 10? And yes, it sure does, because 4 times 15 is 60, and so is 6 times 10. And on this next one, make sure you're trying these on your own first. The question is, does 5/7 equal 7/10? Well, let's do an easy check by cross multiplying. So does 5 times 10 equal 7 times 7? It's very close, but not quite, because 50 does not equal 49. And in this last example, does 3/12 equal 2/8? Well, one way to check is to say, does 3 times 8 equal 2 times 12? And 3 times 8 is 24, and so is 2 times 12. So in this case, yes, those are equal. Now next, let's use cross multiplication to actually solve a rational equation. Okay, now recall, if you multiply both sides by a denominator that has a variable in it, that means you automatically have to check your answers because you may have introduced extraneous answers. Now that doesn't change. Cross multiplication is just a quick way to multiply both sides by the lowest common denominator. So if you don't want to skip that step and you prefer to just multiply both sides by 8x, just do that because it's the exact same thing. Okay, so cross multiplying would give us 3x equals 63 times 8. Okay, now I need to remember I'm going to have to check my answer because I did multiply both sides by that variable x. And now let's simplify. 63 times 8 by my calculator is 504. So we have 3x equals 504. Dividing both sides by 3 gives us 168. So let's check and see if that works. Does 3/8 equal 63 over 168? Well, let's cross multiply and check. 168 times 3, does that equal 63 times 8? And let's check on my calculator. 168 times 3 is 504, and 63 times 8 is also 504. So that in fact does work. So then you can come back here and box that in as your answer. Okay, let's do another one here. Now on this one, when we cross multiply, that's the equivalent of multiplying both sides by 35, by the product of 5 and 7, which has no variables. So technically you don't have to check your answer. You don't have to check your answer, but you can if you want to. Okay, so I'm going to cross multiply here to get 5 times 2x plus 1. That's equal to x minus 3 times 7. Now make sure you have those parentheses around the x minus 3 there. And then from here we can just distribute and solve. So we have 10x plus 5 equals 7x minus 21. Subtracting 7x from both sides, we'll have a 3x over here. And subtracting 5 from both sides, we'll have negative 21 minus 5, that's negative 26. Now 26 is not divisible by 3, so we can leave it as 26 thirds because that doesn't simplify either, negative 26 thirds. I recommend you always leave your answers in exact form. Don't approximate unless you have to. Now, for example, this one, if you do try to get a decimal approximation, you're going to get 8.6666666. The 6's repeat forever. Okay, so this is approximate, not exact. So it's much better to go with the exact fraction version than to go with a rounded version of your answer. So that actually we know is in fact the answer. I don't even have to check because I didn't have any variables in either of those denominators. So I only multiplied both sides by 35, not by any variables. Okay, so now that you've got the basics down, let's start solving some applied problems. Okay, for example, to estimate the number of people in Jackson, which has approximately a population of 50,000, we're going to say, who have had a flu shot. 250 people were polled. Of those polled, 26 of them had a flu shot. So how many people in the city might we expect to have a flu shot? Well, what you can expect is that the same ratio of people who are polled who have had the flu shot is the same as the ratio of people in the entire city who have had a flu shot. In other words, the same percentage of the people polled is approximately going to be the same percentage of the people in the city who have had their shot. So if 26 out of 250 people have had their shot, we can say that's roughly the same as the number of people who have had their shot out of the 50,000. Now we don't know what number goes here, so we actually need to put a variable there. I'm going to call it x. Now never just start using x's without defining it. So let's define x. Let's let x be the number of people in the city who have had a flu shot. You need to be very clear about what your variables represent. So x is the number of people in the city who have had a flu shot. Okay, now that we've defined x, now we can solve. Notice we have two numbers in the denominators, so when I multiply both sides by those numbers, in other words, cross multiply, I'm not multiplying by any variables, so I don't need to check my answer. Okay, now to solve this for x, all we need to do is divide both sides by 250. So I get x is 26 times 50 50,000 all over 250. And I would go to your calculator to see what that is. So 26 times 50,000 divided by 250, I get that that equals 5,200. So the question is, how many people in the city might we expect to have had a flu shot? Approximately 5,200 people we can estimate have had a flu shot. Okay, let's do one involving triangles. Okay, here are two similar triangles, meaning all of their angles are equivalent, which means that the ratios of their sides are also equivalent. Okay, and what I want to do is find this distance here, that length x. Now there's multiple ways to set up ratios here. The ratio of this side on this triangle to this side is equivalent to the ratio of this side to this side. So I'm going to do a couple different methods here. One method is to say x over 15 is equal to 12 over 9. Right? Long side over the leg equals the long side over the leg. And then you could solve from there, and let's go ahead and do that. Okay, you could, again, here we're multiplying both sides by numbers, so no need to check our answer. So we get 9 multiplying, cross multiplying 9 times x equals 15 times 12, and 15 times 12 is 180. Dividing both sides by 9, 18 divided by 9 is 2, so 180 divided by 9 is 20. Okay, so that's the actual answer here. X is 20 units. There are no units specified. Another way to set up your ratio would have been to say that this long side over that long side equals the leg over the leg. So you could have also said x over 12 equals 15 over 9. And you would get the same answer, because if you cross multiply here, you would get 9 times x equals 15 times 12, which is 180. So you get the same equation here either way. Another way to do it would have been to reverse it. Reverse all these fractions and to say, well, 15, or the leg over the long side, equals the leg over the long side. So you could have said 15 over x equals 9 over 12. And then cross multiplying would give you 15 times 12 is 180 equals 9 times x. Same equation. Now this time we would have ended up multiplying by a variable, so we'd be required to check our answer. And there's one last way you could have set up these proportions. Can't see that. And that would be to reverse the second method here. And instead of saying x over 12, you could have said 12 over x. So the long side over the long side, 12 over x, is equal to the leg over the leg, 9 over 15. And again, cross multiplying, you do get the same thing. So when it comes to similar triangles, there's typically 4 ways to set up your equations. I usually try to set them up in one of these 2 ways so that the variables are in the numerator. Just makes it easier to solve for in general. All right, let's do another example. The quotient of a number and 2. So we don't know what this number is, but the quotient of a number and 2 minus a third is the quotient of the number, the same number, and 6. Find the number. Well, we need a variable, and obviously the unknown thing here is the number. So let's let x be the number. And now let's rewrite this sentence or translate it into an algebraic equation that can be solved. Okay, it says the quotient of a number and 2. Okay, the quotient of a number and 2. That means of x and 2. Well, the quotient of x and 2 is x divided by 2. Comma, okay, minus a third. So that would be, here minus a third is minus 1/3. Is means equals the quotient of the number and 16. So the quotient of the number and 16, that's the quotient of x, oh not 16, 6. That's the quotient of x and 6, so x divided by 6. So there it is. We've translated this sentence into an algebraic equation that we can solve. Now this we cannot cross multiply on because we don't have a single fraction on the left side. We're subtracting 2 fractions. So you can only cross multiply if you have a fraction equals a fraction. But because we have 2 fractions, we can't do that. So I'm going to go back to the old method of solving rational equations, and that is to multiply both entire sides by the lowest common denominator. In this case, 2, 3, and 6 of those three numbers, the lowest common multiple is 6. So I'd multiply both sides by 6 to eliminate all the fractions. Distributing that out, we'll have x over 2 times 6, well that's 3x, and 6 divided by 3 is 2. And then on the right side they cancel, so we just have x. Subtracting x from both sides would give me 3x minus x, or 2. Where did I get 2? 3x minus x is 2x, and then minus 2 equals 0. Then adding 2 to both sides give us 2x equals 2. Dividing both sides by 2, we get x equals 1. And since I only multiplied by 6 and no variables, we can stop right there. So the number is 1. Okay, here's another fun example. Andrew and Timothy Larson volunteer at a local recycling plant. Andrew can sort a batch of recyclables in 2 hours alone, while his brother Timothy needs 3 hours to complete the same job. If they work together, how long will it take them to sort one batch? Okay, now problems like this I wouldn't expect you to necessarily be able to solve without seeing an example, because this is a fairly difficult one to read through and understand how to set up. But once you see it, it should make enough sense that you can do other problems that are similar to this on your own. Okay, so what we're looking for is how long will it take them to sort one batch? Okay, so that's what we're looking for. So let's let x, or the variable, be that. Let's let x equal the time, because it says how long it will take them. So the time that it will take them to sort one batch together. Okay, so we have a variable and that's what we're looking for. It says how long will it take them to sort one batch together. Okay, now let's break this down, and the simplest way to break this down is to draw a little chart. Okay, so we're going to need 3 lines here, really four lines actually. I'm going to break it down into what each of them is doing and how long it takes each of them to complete the job. Okay, so it takes, let's see, we have over here Andrew and how, oops, I spelled that, Andrew, and how long it takes Andrew to complete the job. So up here we'll say total time it takes to complete the job. Okay, now it takes Andrew, let's see, to sort one batch of recyclables, he can do it in 2 hours. So it takes Andrew 2 hours, so this will be in hours here, to sort one batch, complete one job. And it would take Timothy 3 hours to complete the same job. Okay, so that's the total time it takes them. But what we're interested in is the total time it will take them to to complete one job together, and that's how we have defined x. If we put the time it would take for them working together on this third row down here. Now we still don't have a way to set up an equation in order to solve for x. So a simple way to think about it is sort of the inverse here. Let's not think about total time it takes to complete the job. Instead, let's think about what fraction of the job can they complete in 1 hour. So on this last column over here, I'm going to put the fraction of the job completed in 1 hour. You'll see why it makes sense to think of this in just a moment. Now, if it takes Andrew 2 hours to complete the entire job, how much of the job, what fraction of the job has he completed after 1 hour? Well, if it takes him 2 hours to do the whole job, he would have completed a half of the job in 1 hour. Okay, it takes Timothy 3 hours to complete an entire job. So the fraction of the job that he will have completed in 1 hour is 1/3 of the full job. And so from these, you can kind of get the pattern here. If you have a 2 here, you're going to have 1/2 over here. If you have a 3 here, you have 1/3 here. So here we have an x, therefore, if it takes you x hours to complete the whole job, then the fraction of the job you complete in 1 hour is 1/x of that. Now, why am I looking at it like this? Because this is how we're going to break it down. The part of the job that Andrew completes in 1 hour, part of the job that Andrew completes in 1 hour. Now, if we add that to the fraction of the job that Timothy completes in the 1 hour, so what I'm saying is, if we think about the fraction of the job that Andrew completed in 1 hour, and we add that to the fraction of the job that Tim completes in 1 hour, well then we're looking at the fraction of the job that they complete together in 1 hour. Fraction or the part, fraction, part mean the same thing. Fraction or part of the job that they complete together in 1 hour. Now this is an equation in words that I can then convert into algebra. Okay, because the part of the job that Andrew completes in 1 hour we know is 1/2. The part of the job Tim completes in 1 hour is 1/3 of the full job. And so the part of the job that they complete together in 1 hour is 1/x of the job. We already know that. Now we have an equation which we can then solve for x. Now this one again is similar to the previous one in that we cannot just cross multiply right off the bat, and that is because we have 2 fractions on the left side, not just 3, not just a single fraction. So instead I'm going to need to multiply both sides here by their lowest common denominator, which between 2, 3, and x looks like it would be 6x. So I'll multiply the left and the right by 6x. On the left, 6x times 1/2. 6 over 2 is 3, so we'd have 3x. Plus, okay, 6x divided by 3 is 2x equals, and on the right the x's cancel and we get 6. So simplifying here, we get 5x equals 6. Dividing both sides by 5, we have 6/5, which in an applied problem makes more sense to think about as a mixed fraction, which is 1 1/5. Okay, so that then, x is 1 1/5, and recall x was the time it will take them to sort one batch together. So therefore it'll take them 1 1/5 hours to complete the job together. Always interpret your answers to applied problems. Okay, let's do another example. This again is one that you might not get on your own if you'd never seen an example like it, but I'm going to show you an example so that you will then learn how to solve very similar problems. Okay, a car travels 600 miles in the same time that a motorcycle travels for 50 miles. If the car's speed is 15 miles per hour more than the motorcycle's, find the speed of the car and the speed of the motorcycle. Okay, so what we want to find is the speed of each. Well, we need a variable here, and let's see which one travels slower. The car says the car's speed is 15 miles per hour more than the motorcycle. The motorcycle travels more slowly, so I'm going to let the variable, or x, be the speed of the motorcycle. Okay, the reason I'm doing that is because then it says the car speed is 15 miles per hour more than the motorcycle, so then x plus 15 would be the speed of the car. There's no reason to introduce two different variables for the two different speeds because it's easy to write them both in terms of the same variable. And we don't really know how to deal with two variables yet anyways. Okay, so x is the speed of the motorcycle. If we let x be that, then x plus 15 would be the speed of the car. Now you could have set it up differently. You could say, let's let x be the speed of the car, then x minus 15 would be the speed of the motorcycle. And you would get the same solution in the end. Your work would just look a little bit different. So, but that would be okay too. Okay, now the one equation that you need to know, the one relationship here you need to memorize right now if you don't know it, is that the distance something travels, if it's traveling at a constant speed, as we're assuming that these, the car and the motorcycle are, that the distance is traveled is equal to the rate, or the speed, in other words, at which they're traveling, times the time for which they travel. Okay, this is often written d equals rt, distance equals rate times time. Okay, we do need to know that relationship in order to set up the equations to solve for x. Okay, now it says a car travels 600 miles in the same time that the motorcycle travels 450 miles. Okay, so let's look at the car and the motorcycle separately. So first let's look at the motorcycle over here. Make sure you label which one you're working with. So I'm working with the motorcycle. Label that. Now the motorcycle, let's see, let's write this equation out for the motorcycle. Okay, now we know that the motorcycle can travel 450 miles in the same amount of time that the car travels 600 miles. So the distance that the motorcycle travels in this problem is 450 miles. We'll leave off units until the very end. Is equal to, that's the distance, is equal to the rate at which the motorcycle travels. Well, the speed of the motorcycle is x, times the time for which the motorcycle travels, and we don't know what that is. So I'm going to call that t sub m, meaning time for the motorcycle to travel. Okay, now let's go over here and let's look at the car. The car can travel 600 miles, so that's its distance, is equal to its rate. Well, the rate at which the car travels is x plus 15. Make sure you don't forget those parentheses. Times the time for which the car travels, and we don't know what that is either. However, what we do know about the times is that they travel these distances in the same time. Okay, the car travels 600 miles in the same amount of time that the motorcycle travels 450 miles. Meaning, the time that the motorcycle travels, the amount of time that it travels for, is the same that the amount of time the car travels for. Those times, that's a C there, those times are equal. So if we solve both of these two equations here for the t, then we can set them equal and solve. Okay, so to solve this motorcycle equation for t sub m, we would need to divide both sides by x. So we get t sub m equals 450 over x. And over here to solve for t sub c, we would divide both sides by the whole quantity, x plus 15. So we'd get 600 divided by x plus 15. And now those are equal, so let's set them equal and solve. So we know that 450 over x is equal to 600 over x plus, oops, that should say 15, x plus 15. Now we have an equation which we can solve for x. Now the hard part on these applied problems is getting to this point, getting to the equation that you can then solve. Solving is usually a little easier. In this case, at least we can cross multiply because we only have a single fraction and a single fraction. So we have 450 times x plus 15 is equal to 600x. And then we did multiply by variables, so I'm going to make a note, meaning we have to check our answers because we multiplied by x's there. And now solving, we'll get 450x plus 450 times 15. Do that on your calculator. 450 times 15 is 6750. That equals 600x. Subtracting 450x from both sides, we have 6750 equals 150x. And dividing both sides by 150 gives us 45. Therefore, x is 45. Okay, now remember we do have to check, so let's go check that first real quick. So I'm going to plug it into this equation up here and see if 45 does in fact work. Okay, let's simplify this first. 45 or 450 over, actually this one's so easy to simplify without cross multiplying. I'm just going to simplify this fraction. 450 divided by 45 is 10. And then on the right side we have 600 divided by 60, which is also 10. So that's a true equation, so it does work. Okay, now the answer is not x equals 45 because the problem did not even have x's in it, so we do need to interpret the answer. It says find the speed of the car and the speed of the motorcycle. So we got that x is 45 and we defined x to be the speed of the motorcycle. So therefore the speed of the motorcycle is 45. So let's write that out. Is 45. Now units here. The distances given in the problem were in miles, and the times I would assume are miles per hour. Okay, because we let the car's, and I'm not assuming actually, we let the car's speed be in terms of miles per hour. So because this is a speed, its units are miles per hour. Now if the motorcycle is traveling at 45 miles an hour, then the car is traveling 15 miles an hour faster. So the car is traveling at 60 miles an hour. And there is our answer. Okay, there's a few practice problems in your homework for you to try these with. I know these are a little bit challenging, but once you do a few and do enough of them until you get the processes down on these applied problems, then you'll be good to go.